So the value of m that we're given here, we see its direction. It's making it smile, so it's a positive 75 Newton meters. And we want to know the stress at B and the stress at C due to this bending moment. And note in the picture there is no internal normal force here, which is also a normal stress. And what we'll find when we do combined loading towards the end of the semester is we could have bending and a internal normal force, both of which are going to induce a normal stress that will be additive. Right? But here we just have the bending moment. All right, so the equation we're going to use eventually, we'll see how we get there, is that the bending stress is negative my over I. We know the m value. The y is easy enough to find. We'll get that from the cross section. So really it's this I value. We were not given it for this material. So we're going to have to find it for this cross section. We're going to have to find it for this cross section. So to do that, we have to dig back into what we did in 211, and this is where we finally get to apply the area moment of inertia that was kind of just a fun exercise in 211. Now you see what the point of all of that was. So we have our cross section here that looks like pi. So everything's in millimeters here. I just won't keep writing millimeters. As we saw in 211, if we want to find the moment of inertia, well, first thing what we need to know is where's the neutral axis located? Because to find y, we need to know our distance from that neutral axis. And again, the neutral axis is just, it coincides with the centroid. So somewhere along this is the centroid of the shape, and that's going to be the neutral axis. That is where there is no, when it bends, this plane does not contract, it does not expand. I'm going to assign my coordinate system with its origin at the bottom here. So the distance between the neutral axis and the horizontal axis, that's going to be my y bar. That's how do I get to my centroid? So remembering back to 211, I want to break this shape into easy to identify pieces, in this case rectangles. So I'm going to make one horizontal rectangle across the top, and then two vertical rectangles, 2 and 3 here. Right, so the first step is we need to find where the centroid is, again, which is the same as the neutral axis for this. So for each shape, we want to find each shape's area. For shape number 1, it's 10 millimeters high. It's 80 millimeters wide. So the area is going to be 800 square millimeters. Shape number 2 and shape number 3 are both 40 millimeters high by 10 millimeters wide, so 400 millimeters squared for each of them. So the total area of my cross section, 1,600 square millimeters. We then want to find y tilde, so that is the distance between the shape's centroid and the coordinate system, the origin of the coordinate system. So remember, for a rectangle, the centroid is at half of its height. But we have to measure that vertically to the x-axis. So to go from the x-axis to the centroid of shape number 1, I have to go up by 40, and then I have to go up by another 5 millimeters. And it's in the positive direction. So y tilde, 45 millimeters above the x-axis. For shapes 2 and 3, to get to its centroid, at its center, I start at the x-axis and I have to go up by 20. Last step, I multiply A times Y tilde across my rows. So I get 36,000 and 8,000 for the other two. And to find Y bar, the location of that centroid, it'll be 52,000 over 16,000. I'm sorry, over 1,600. Y bar is going to be 32.5 millimeters. Okay, so I need that to find the Y over here. But I also need that to do the next step, finding the value of I, find the value of that moment of inertia. I expand my table. I want to know now for each shape, what is its area moment of inertia about its own centroid. And then we have to use the parallel axis theorem as well. Since the centroid of each of my small shapes is not the same as the neutral axis. 1/12 BH cubed. And remember, that's for a rectangle. Remember, more importantly than knowing is it B cubed or H cubed, remember the dimension that's cubed is going to be the dimension that is perpendicular to the axis we're bending about. So in this case, we're going to be bending about this horizontal axis. So we want to cube the vertical dimension. So for shape number 1, it'll be 10 cubed times 80 over 12. And for shape number 1, that'll be about 6,667. This is in millimeters to the fourth. For shape number 2, again, it's the vertical dimension that's going to be cubed. So for shape 2 and 3, it will be 40 cubed times 10 over 12. So that'll be roughly 53,333. So the total, 113,333, adding the three shapes together. Again, this finds the moment of inertia of each shape about its own centroidal axis, but because that is not the same as the neutral axis of the composite shape, we have to use the parallel axis theory, where that's where we apply this AD squared term to make the adjustment to these numbers. So the way I presented it in EMCH 211, we want to find this distance between the neutral axis or the centroidal axis of each shape and the neutral axis of the composite shape. So really, it's just going to be Y tilde minus Y bar. So all the information's already down there. We just want to write it down. So that's 12.5, negative 12.5, negative 12.5. The sign on the value of D does not really matter because all we're doing is squaring it in the next term anyway. The last column, this is where we do the parallel axis adjustment. It's the area of the shape times the value of D squared. So we get 125,000 for shape number 1. 62,500 for shape 2. And since these are the same shape, again, 62,500. If we add up all the AD squared terms, we get 250,000. The last step, to find now the moment of inertia of the whole shape about its own centroidal axis, we add up this 113,333 plus the 250,000. We get 363,333 millimeters to the fourth power. But as we've been doing the whole semester, I want to be working all in base units. So I want to convert this to meters to the fourth power. So I have to divide this by 1,000 to the fourth power. So in meters to the fourth power, this is 3.63 times 10 to the negative 7 meters to the fourth power. So having it in the base units will make it easier once I go and find the stresses. All right, we have the value of I. We were given the value of m. So now we can go about finding what is the normal stress at the points, in this case, C and B. All right, so let's start with point B. So negative, m is a positive value, 75 Newton meters. For point B, which is located at the top left point here, its value of y, remember in this formula, in the y in the my over I, y is the signed distance between the location of the point we want to know the stress at and the neutral axis. So the y value for here will be this distance, and we're above the neutral axis, so it's going to be positive. Right, to find that, we know that the neutral axis was located 32.5 millimeters above the bottom of the piece. Point B is located at the very top, which is going to be 50 millimeters. Right, so the distance between point B and the neutral axis, 50 minus 32.5, that's this distance. It's positive, and I want to convert that to meters, so it's times 10 to the negative 3. That way, this is in Newton meters. This is now in meters, and my value of I has been converted to meters to the fourth power. Right, finally, I'm dividing this by the value of I that we just found, 3.63 times 10 to the negative 7. Meters to the fourth. We have a negative, a positive, and a positive. We're going to get a negative value here. When we work this all out, we have newtons times meters squared divided by meters to the fourth, which is going to be newtons per meter squared, which is a Pascal, which we should expect because it's a stress. So at point B, we're going to get negative 3.62 megapascals. Again, our interpretation for the normal stresses, negative means it's in compression, positive would be tension. Right. Second, we can find the stress at point C, which is closer to the neutral axis. Right. The moment is still 75 Newton meters at this vertical slice. But point C is only located 40 millimeters above the x-axis. But the I value is identical. So calculating our stress at point C, we should expect it to be lower, and it is. The m is the same, I is the same, it's just the y that's different. It's only negative 1.55 megapascals. Also compression, since again we're above that neutral axis.